wonderful? Okay, so I want to give you a few more of these applications, and the first one is just a variant of Marshall-Hall's theorem, and it's the statement that finitely generated subgroups. So this is application 2. Finitely generated subgroups of Fn are separable. Okay, and what that means is that if H is a finitely generated subgroup, and if G is some element in the complement, okay, so I take some element that's not in H, then there exists a finite index subgroup H prime, such that H prime contains H, and G is not in H prime. Okay? In other words, if I take the intersection of all finite index subgroups that contain H, I will get exactly H, not anything else. Okay? And that's expressed by saying that finitely generated subgroups of Fn are separable. You can separate them from elements. This is like in topology, when you separate closed sets and points or whatever. You can separate a finite index subgroup from any element outside by a finite index subgroup. And what is the proof? Well, the proof is the same. I shouldn't have started erasing it. But the proof is the same, and maybe schematically I will, okay, let's just erase this, and I will just draw a schematic picture. That I made a big mess here. Oh well. Okay, so I'll just say same proof. And here's the schematic. So here's my graph that represents H, right? It immerses to the, there's an immersion to the rows, and there's a base point, and now I can look at where G is, right? So G, just like in these examples with A, B, right? I can start developing G in my cover, and maybe it'll stick out like this. So here's G. It's not, G is not in H, so whatever G is, it's not going to all come back all the way to the base point, right? And this picture still immerses into this graph. Even the extended picture like this, it still immerses. This is really part of the covering space corresponding to H. So here's an immersion of graphs. Now complete it to a covering space. Complete to a covering space. And that's it. When you complete it to a covering space, that's your H prime. It contains H, obviously, and it does not contain G, because G doesn't close up in H prime. End of proof. Is that clear? So it's just a variant of the proof of Marshall-Hall's theorem. Okay? Okay, number 3. The free group is Hopfian. And what that means is that every epimorphism, say F from Fn to Fn, is also injective. Okay, so not all groups are Hopfian. There are many groups that are not, where you can have a self-epimorphism which is not injective. The simplest example is so this is called the Baumstock-Soliter group 2,3. So this is given by presentation like xt t inverse x squared t equals x cubed. This group is not Hopfian. Okay, so there are kind of relatively simple looking groups that are not Hopfian, but the ones we like tend to be Hopfian. So a free group is good. Okay, so how do we prove this? Okay, so it's again folding. Everything is folding, free groups. You can invent your own theorem and prove it. Okay, so how do we do this? Well, we start with the same picture, right? Here we had a particular 3 elements that generated H, and we constructed a homomorphism that really goes from F3, right? Fundamental group of this graph is really F3. And the homomorphism was chosen so that it sends the first generator, this morphism was chosen so that it sends this first generator AQB. The first generator of the free group F3 goes to this element in the free group of rank 2. And the second basis element goes here, the third one goes here. So we can do this with automorphisms as well. So like if I take, let's say I take an automorphism of F2, or epimorphism of F2, that takes A to AB and B to BAB, for instance. Here's an example. Right, so what would I do? I would take this picture, and I would subdivide this edge into, there's A and there's B like this, and then this one gets subdivided into 3 pieces. There's a B, okay, BAB, so BAB like this. So this gives me a morphism to the rows, right? Okay, so given an automorphism, or given a self-epimorphism, or any endomorphism if you want, any homomorphism from free group to free group, you can represent it like this. Right? I just look at where the first generator goes, and I represent it by, I subdivide this loop into so many pieces, and I label according to the word, and I get a morphism like this. And now I start folding. Now you can, maybe you can do this as an exercise. Here, the 2 B's will get folded, and then I guess the A's will get folded, and then the B's will get folded again. So this would get decomposed into a product of folds, right? And then the last map would be, so this is gamma 1, this is gamma 2, gamma 3, and then you would get, maybe we should call it gamma K. So there is a factorization like in the Stallings theorem, and it would go to the rows. Right? So this is a factorization like in the Stallings theorem. Okay, now what can we say about this? First of all, what is this last map? It's an immersion, but what else can we say about it? Given that the map is given map is an epimorphism. We started out with an epimorphism. So what can we say about this last map? What? It's a homeomorphism, right? It's generally an immersion, but if it's not a homeomorphism, then it would be, the image would not be the whole group. This map would not be epi. Remember, the image in pi 1 of the original map is the same as the image in pi 1 of the last map. So it has to be the whole group. Well, if it's an immersion that's not a homeomorphism, then the image in pi 1 is not everything. Right? So what could it be? It could be a covering map, a non-proper, not a homeomorphism, but a covering map. But then the image is a finite index subgroup and not the whole group. Or it could be that it's not even a covering map. But then you certainly have, there are elements that are missing, because you can go to the place that has, where their outgoing edge is missing, and then you can, that's why you can find elements that look like this. Right? If there's a place where their edge is missing, then you can just go there, and they'll give you elements that are not in the subgroup. Right? So if you have an immersion that is not a homeomorphism, then the image in pi 1 is not the whole group. It's not onto in pi 1. So as a consequence of the assumption that that f is since f, so let's call this G, right? Since f sharp, or I guess it's just called f, is epi, G is a homeomorphism. Okay, so that means that the rank of gamma k is equal to n. The rank of the last graph is equal to n because this is a homeomorphism. And this is the same as the rank of the initial graph. The initial graph was also of rank n. So what does that mean? How many type 3 and 4 folds do we have? When we do type 3 and 4, the rank goes down. When we do 1 and 2, it stays the same. Well, we started with n, and we ended with n. So that means we don't have any type 3 and 4 folds. So all folds are of type 1 and 2. But those are all isomorphisms in pi 1. So that means that the original map is also an isomorphism in pi 1. And so is that. Okay, that's the end of the proof. Is it okay? So maybe to say the argument one more time, we know that the given map is onto in pi 1, so that means that the last map, the immersion, also must be onto in pi 1. The only way an immersion can be onto in pi 1 is if it's a homeomorphism. Yes?
Is the type 1, 2, 3, 4 is all of the type of the immersion?
Yes, although there is this issue with, that somebody pointed out that you can, but this requires subdividing. So if you take a I mean, so I said let E1 and E2 be two oriented edges with the same endpoint. Well, it could be that it's the same topological edge with two different orientations. And then what you would be doing is squashing a loop. You would have a loop and you would be squashing it to a line. Okay, so you could call that type 5 if you want. But this is, I was imagining that E1 and E2 are distinct topological edges. And then they're oriented so that they have the same initial point. But you could also, I mean, you could also just subdivide if you have this, so E1 is this, this edge oriented this way, and E2 is this oriented the other way. Then I guess the recipe would say just squish it, and you will get this. But you could also just subdivide this whole loop and call it two different edges, and then this would become a type 3 move. So okay, so it just depends on definitions. But yes, the way I had it set up is those four types are the only ones. Okay. Yeah, okay, so just to recapitulate this. So this G must be a homeomorphism, and that means in particular that the ranks of the graphs at the beginning and at the end are the same, and that means that there are no type 3 and 4 folds. And that implies that all these folding maps are isomorphism in pi 1. There's actually I mean, I can give you a little exercise. This is somewhat an overkill. So a group is called residually finite if the trivial subgroup is separable. In other words, if the intersection of all finite index subgroups is the trivial group. I made more mess. Okay, so a group is residually finite if a group G, if the intersection of H, so that H and G has finite index, is 1. Okay, so that's a weaker property than the one that we already have here, that finitely generated subgroups are separable. This just states that the trivial subgroup is separable. Okay, and then the exercise is that if G is finitely generated, plus residually finite. This implies that G is Hopfian. Somehow the punchline is that finite groups are Hopfian. That's just set theory. If you have surjective map, surjective function from a finite set to itself, then it's also injective. Okay. All right, so now we'll get to something related to, this is going to be our first theorem about automorphism group of the free group. And it's the one that was proved by Nielsen. Although I'll just think about the generating set rather than the whole presentation. Okay, so so this is the fourth application, I guess. This is the theorem of Nielsen, 1924. And here we'll take the whole. We won't worry about mounting out by inner automorphisms. The whole automorphism group is finitely generated by the following automorphisms. Okay, so we have the permutations of the basis elements. Okay, and then we have sign changes. So I guess I'm calling the basis AI, so I from 1 to n. So I can map AI to AI inverse, or plus minus 1 maybe. So for every I you pick a sign. So so 1 and 2 together generate what's called a sign permutation group. Okay. And then there are automorphisms. So these are called Nielsen automorphisms. Where well, I'll just give you one of them. One of them suffices. But you can, so A1 goes to A1, A2. And then the other AI just go to AI. More generally, Nielsen automorphism allows you to change these indices from 1 and 2 to something else. But in the presence of the sign of the sign permutation group, you don't need these others. You can, if you want to switch 3 and 4, then you would first permute. You take a permutation that takes 1 and 2 to 3 and 4. In other words, you would conjugate this guy here by some permutation, and you would get Nielsen automorphisms with different indices here. You can also put A2 on the left. So this is not a commutative group. So A1, A2 is different from A2, A1. But you can also accomplish that by taking inverses, right? If I take A1, A2 and then take the inverse of this, there will be A2 inverse, A1 inverse. And then by the sign permutation group, you can also change the sign of the A1 inverse and A2 inverse. Okay, so just this one is enough. Okay, so I'm going to, for the rest of the hour, I'm just going to sketch the proof of this using folding. Okay, so the main notion in the proof is that of a change of a maximal 3 automorphism. So that's what we have to understand first. So I'm going to talk about the change of maximal 3 automorphism. Okay, so what are those? Okay, so maybe I'll take a different pen. Okay, let's continue with the blue. Okay, so gamma is going to be a graph, and then we'll have two different maximal trees. T1 and T2 are two maximal trees in gamma. Okay, so now labeling and orienting edges outside of T1 and T2 give identifications. Okay, so I have pi 1 of gamma with the base point, some base point v0, and here is Fn, and I have a particular isomorphism which I will call phi T1, even though it depends on more data than just T1. It depends on the labeling and orienting of the edges outside of T1. Okay, so this is my isomorphism to the free group. You choosing T1 as my maximal tree. I'm happy to live with the ambiguity of so what happens to the identification if I decide to change the orientation of one of the edges? How does the identification change? It's a sign change, exactly. When I change the orientation, then one of the labels is going to be sent to its inverse, which is a sign change. So I already have that in my pocket, so I don't really want to worry about that too much. Similarly, if I choose to relabel the edges, that's going to correspond to some permutation. So I don't want to worry about this. So I'm really thinking about the maximal tree here. Okay, and then you have the other one as well. And then here I have the identity, of course, right? And composing this gives me some automorphism here, and that's called the change of maximal tree automorphism. Okay, by definition. So something is some automorphism between free groups is called the change of maximal tree automorphism if it fits in the diagram like this. So you can pick two maximal trees, and you can construct a diagram like this. Then your automorphism is a change of maximal tree automorphism. Okay? Okay, so the main example of such automorphisms are Whitehead automorphisms. Okay, so this is the case when T1 and T2 have one edge. Okay, so if you have a graph where a maximal tree has one edge, then you know what the graph looks like, right? So there are two vertices, and then there's a bunch of edges joining them, and then there are a bunch of loops. Maybe I'll just draw one. Maybe I don't want to do too much, so maybe I'll just three edges like this. There could be you can have any number of edges joining the two vertices and any number of loops going around like that. And maybe this is V0. And then I have a maximal tree. I have two different maximal trees. So two of these edges, of these vertical edges, can be chosen to be the maximal tree. So here's one of them. Okay, and here's the other one. This is maybe T1, and this is T2. Okay, and then I can choose labeling to make my computations easier. I mean, any labelings are just going to differ by sign permutation. So this is going to be A4. This is A1. So generally speaking, all edges are going to be oriented away from the base point. except when I decide to change the maximal tree, I'm going to swap it with A1. So then A1 will go backwards this way. But all the other edges will go the same way as before. Okay, so everything goes away from the base point except for the edge that I swapped for when I change the maximal tree. Okay, so now what is the automorphism here? Well, where does A1 go? Well, in this picture here, A1 is represented by the loop that goes up this edge A1 and then comes back along the maximal tree. Okay, that same loop over here also reads off A1. So A1 goes to A1. This is why I chose things the way I did, so that A1 just gets fixed. What happens to A2? Well, A2 is this loop here. Goes up on A2 and then comes back on T1. So this goes to A2A1. You see that? So this is really, it looks like a Nielsen automorphism. Where does A3 go? Well, I'm going up on the red and then do A3 and then come back on the red. So over here, that's going to mean A1 inverse, A3, A1. And then A4 is A4 just goes to A4. Okay, so that's what a Whitehead automorphism looks like. There's some kind of a special generator, in this case A1, which is fixed, and then all the other generators either get multiplied only on one side by either that letter or the inverse in general. Here we cleverly chose things so that it's just A1, not A1 inverse. Or it's fixed, or it gets conjugated by that letter. Okay, so that's what a Whitehead automorphism is. There's a special letter which is fixed. All the other letters either get multiplied by the letter or the inverse on the left or on the right, or they get conjugated by the special letter. Okay, so that's the Whitehead automorphism. And the exercise is that the exercise is that this is the Whitehead automorphisms can be expressed as a composition of 1 to 3. Okay, so I won't do that, but that's some kind of a, this part is already on the list, and then for this one here, you have to replace A2 by A3, and you can multiply it by A1 on the right, and then you can multiply it by A1 inverse on the left. Okay, so Whitehead automorphisms are generated by these things over here. Okay. And then another fact, easy fact, exercise. There are lots of exercises. So if T1 and T2 have all edges in common except one, all edges in common except one, then the associated change of maximal tree, the associated change of maximal tree automorphism is Whitehead. Why is that? Well, because if they have edges in common, you can just collapse them. That doesn't change the identification with the free group, and so then you're just left with one, with this picture. Okay. Now the next thing is that's also, I'll also state it as an exercise. It's good to have exercises. I guess you can read it as an outline of the proof if you want, but they're not very hard, and I'll say some words about this. If I suppose I give you two maximal trees, so T1. So if T1, well, let's say T and T prime are two maximal trees in gamma, then there is a sequence. T equals T0, T1, Tm, and Tm is equal to T prime. So of maximal trees. so that ti and ti plus 1 differ in only one edge. So the analogy is with bases of vector spaces, right? If I give you two different bases of a vector space, you can do this. You can do swapping, right? This is one of the first things you prove in linear algebra. You take a vector in one basis that's not in the other. You can remove it, and you can add to this partial basis now. You know, there's one vector missing. You can add some vector from the other basis and get a new basis. So you can go from one basis to another basis by this kind of swapping operations until you know. So any two consecutive bases in your construction will differ in only one vector. And this is analogous, except for instead of a basis, you have these maximal trees. In fact, there is an abstraction of this which is called a matroid. There's some combinatorial thing that it's a collection of finite sets with exactly this property, that you can go from any one to any other one by doing these swaps one at a time. That's the main axiom for matroids. Yes.
What is the exact definition of white-hat automorphism?
So it's a change of maximal tree automorphism when these two trees have only one edge. When the maximal trees have only one edge, then it's called a white-hat automorphism. So then the graph necessarily looks like this. If a maximal tree has only one edge, then the graph has only two vertices, and this is the picture. Okay? Okay, so modulo these exercises, the corollary is that every change of maximal tree, every change of maximal tree automorphism is a composition, is a finite composition of 1 to 3. Right? Because any change of maximal tree automorphism can be written as a composition of things where you do one at a time. And those are white-hat automorphisms, and these white-hat automorphisms are also compositions of 1 to 3. Right? All right, so now we're more or less ready for Nielsen's theorem. Are there any questions here? Okay, so let's do proof of Nielsen. Okay, so we start with any automorphism. Let F be any automorphism Fn. Yeah, I guess you should pause and think about what, like this sort of thing may be the first example of an automorphism that you can think of that has infinite order. Right? I mean, you can think about sign permutations, but there are a lot more automorphisms in the free group than just sign permutations. Right? The group of sign permutations is a finite group. On the other hand, out Fn is an infinite group, and it's a very big group. Okay, so let's fix an automorphism, and I'm going to, as usual, I'm going to consider a morphism of graphs So this is going to be from gamma to R. So R is going to be rows. So from a subdivided rows, gamma. So gamma is just going to be rows, but I'll subdivide according to where the generators go. From subdivided rows gamma to the rows R. Representing F. And by abuse of notation, I'm also going to call it F. Okay, maybe this should be F sharp or something. Okay, so this is what I was, at the end of, or maybe beginning of this hour, I don't know. Like A goes to AB. For some reason, this is my favorite automorphism, or at least at this level. So here you would draw a picture like this, right? It would be, this loop would be subdivided into 2, this one would be subdivided into 3, and it would go, right? That's what you're supposed to imagine here. Given an automorphism, I construct this morphism of graphs. Okay, now we're going to factor it into faults, because that's all we know how to do, right? We have this morphism, we factor it into faults. This is automatic. Okay, so factor it into faults. Okay, so it's gamma to gamma 0 to gamma 1 to gamma k to r. Now the last map is a homeomorphism. We already know that, we discussed that, right? The last map is a homeomorphism. Right? For an automorphism, the last map is a homeomorphism, and all folds are of type 2, 1 and 2. Okay, that already came up in the proof of Hopfian. Right? So far so good? Okay. Okay, so now the main claim is that given any one of these folds, if I choose my trees carefully, my maximal trees, so this is the main claim. For any of the folds, say gamma I to gamma I plus 1, after choosing maximal trees, say Ti in gamma I and Ti plus 1 in gamma I plus 1, carefully, the induced map, the induced homomorphism in pi 1 is well, I'll just say it's generated by 1 to 3. In fact, it's a Whitehead automorphism, but so in fact Whitehead. Okay, so why is that? So we kind of already touched on this at the very beginning. So any one of these folds is type 1 or type 2. So let's say it's type 1. So then I have this picture. Right, this is gamma I, and this is gamma I plus 1. And I'm allowed to pick a forest here and a forest here, and then I look at the induced map in pi 1. Well, I'm going to pick a maximal tree to include all these, both of these edges. And I'm going to take the image over here. And then what is the induced map in pi 1? If I choose labeling the same way. What? It's an isomorphism, but more than that. So maybe we should do an example here. I don't know. Should I just do this? Okay, let's just keep it simple. And this is my base point. Okay, so I'm going to choose the labels. So the maximal tree is just this red, what you see red here, just to keep it simple. And I'm going to put A here, B here, C here, and I'm going to do the same thing on the other side. Okay, so what is the map here? Where does A go? A goes to A. Where does B go? B. Where does C go? In fact, here it's identity. So if I choose cleverly my trees and labelings, then in fact in this case I get identity. No, so this is type 1. It's a little more complicated if it's type 2. Because then I cannot do this. I don't know. Okay, let's just do an example again. Here's my base point, and I'm going to identify, the fold will identify this edge and this edge. This is I don't know, this is my E1 and this is E2. I don't know, E1, E2. So I'm really wrapping this around here. So I'm just going to get the rows. And the maximal tree, well, there's only one maximal tree here. There's nothing else I can do. And I'm going to label this to be, A, and this is to B. That's A, that's B. Okay, so what is the map now? Well, A still goes to A, right? And where does B go? Okay, I didn't give you the orientation. Well, I did give you the orientation, like this. I didn't give you the orientation of this guy. Oh, I did, sort of. Okay, so where does B go? B is, you go up here, you do B, and then come back. Okay, so, but this edge gets identified with A. Right, so it's really A, B, A inverse. But that's a Whitehead automorphism.
Professor,
yes.
A inverse be A?
Well, okay, so this now depends on how you choose orientations. You're traveling from here along this edge, which, the way I chose orientations, this gets identified with this. So after the identifications, you're really traveling this way, which is A. You're first doing A, and then you do B, and then you come back, which is A inverse. But if you could orient it the other way, and then it would be A inverse BA. But either way, it's a Whitehead automorphism. Or you can, another way to do this is to subdivide, and so not work with type 2 automorphisms at all, or folds at all. Whenever you have a type 2 fold, you introduce an extra vertex, and you declare that you really did a composition of 2 type 1 folds, and then you don't really have to worry about this. But anyway, it's nice to see this directly. Okay, so this is one thing that we that if you choose these trees carefully, then going from gamma I to gamma I plus 1, after identifying with the free group, that automorphism is on our list, or it's a composition of things on our list. But now we still have the issue of that we there are 2 maximal trees in gamma I. One that's needed for going from gamma I minus 1 to gamma I, and one maybe a different one that's needed for going from gamma I to gamma I plus 1. So we need to compose those 2, but those are those are exactly change of maximal tree automorphisms. And that's the end of the proof. Maybe I'll write down some words here. Okay, so so each gamma I now has two maximal trees, one corresponding to the fold gamma I to gamma I plus 1, and the other corresponding to the fold gamma I minus 1 to gamma I. In fact, maybe maybe I'll call it AI. This first one is AI, and the second one is BI. Okay, so then what I really want to think about is, you have gamma, which maybe this should be thought of as being gamma minus 1 or something. I should have called gamma 0 or something. Anyway, let's just draw a portion of this factorization. So this is a piece of the factorization, and I want to stick in these trees, maximal trees. So over here I have gamma I minus 1, bi minus 1. That's the one that's needed for the fold, that follows, right? The b's are the trees that are needed for the fold that follows, and the ai's are the trees that are needed for the preceding fold. So here I have gamma I minus 1, bi minus 1. Over here I have two of them. I have gamma I ai, and then I also have gamma I bi, and then I have gamma I plus 1 ai plus 1. Okay. So each of these is identified. Pi 1 is identified with the free group. There's an identification with the free group that comes from the choice of the tree. Okay. Now here we have the fold. This is my fold over here. And what we just did, what this main claim says that when you make this diagram commute, the associated automorphism here is Whitehead. In fact, most of the time it's just identity. If you get rid of these type 2 folds, then this is just always identity. So this is Whitehead, and likewise this is Whitehead. But what is this? This is the change of maximal tree, right? Change of maximal tree. It's the same graph, but two different trees. And so what you insert here to make the diagram commute is also a composition of automorphisms on our list. And so all of these are compositions of things on our list, and so the whole thing is, this F, the original F is a composition here, and so that's also a composition of things on the list. And that's the end of the proof. Should I repeat this? Did you follow? Yeah, this is maybe this theorem is harder than the ones they did before. But let's see. So this is also a fold. So I have this sequence of folding maps between graphs, and I want to kind of get an induced sequence of automorphisms of the free group. But to do this, I really have to identify each of these graphs with the free group, and for that I have to choose a maximal tree. And so according to this main claim, I can, if I choose trees carefully, then the maps induced by the individual fold are going to be very simple. But the price I have to pay is that, for the same graph, I'll have two different trees. One for the preceding fold and one for the one that follows. And so I have to then worry about changing the, going from one tree to the other. And that was somehow what the main work was. That somehow when you do this, when you change the maximal tree, what the automorphism you get from this change of maximal tree is a composition of things in our list, because it itself is a composition of finitely many Whitehead automorphisms. You can go from AI to BI by swapping edges one at a time. And every time you swap one edge, you remove one edge and you insert another edge, well, that associated automorphism is going to be Whitehead by definition. And so you can go from AI to BI by finitely many such operations. So that means that whatever this thing is, it's a finite composition of Whitehead automorphisms. Yeah.
So basically, the reason that we are having only type 1 and 2 folds are precisely because we should not use the rank.
Exactly. Yeah. So we know since it's an automorphism, that last immersion must be a homeomorphism. So the rank of all these graphs is constant. It doesn't go down anywhere. Any more questions? Yes.
Is that automorphism group is finitely presented?
It is finitely presented. But somehow to list all the relations is not all that simple. In fact, I don't know it offhand. I would have to look it up. But it is finitely presented, and one can. There is a 10-page paper that does this from the fairly modern point of view. It's easier once you know about outer space. For example, once you know about outer space, then it's more or less obvious that the group is finitely presented. It's not obvious what the presentation is, but it is obvious that it's finitely presented. So I'm going to discuss a little bit of that tomorrow. Tomorrow's main topic is outer space. I don't know how much we'll be able to prove, but we'll say something. Yes.
None of those
Nielsen automorphisms, yeah,
are inner morphism. Inner automorphism.
No, they're not. They're not inner automorphism. So you can see they're not because B, like A goes to A, B goes to AB. You see that B doesn't go to a conjugate of itself. AB is not conjugate to B. Inner automorphisms always send an element to a conjugate of itself. B and AB are not conjugate. So this is definitely not an inner automorphism. In fact, this automorphism has infinite order, right? Because if I take f to the n, it's going to send B to, every time you apply f, this B is going to put out another A. So this will be A to the n B. And none of these are conjugate to B. So in fact, this automorphism has infinite order even as an outer automorphism. Even when you mod out by the inner automorphism group, this element will have infinite order.
Sorry,
yes.
I mean Nielsen automorphism and sign permutation group. Sign changes and permutations.
Yes.
Are inner automorphism.
Well, no. I mean, if I swap A and B, that's not an inner automorphism, right? That if I square it, I'll get the identity, which is an inner automorphism. So this element has order 2 in out Fn, but it itself is not inner because A and B are not conjugate. None of the technically the automorphism like A goes to A and then B goes to A inverse BA and C goes to A inverse CA. That's technically a Whitehead automorphism, and this one is a conjugation by A. So some of the Whitehead automorphisms, I guess, are if they look like this, then they're inner. But most of them are not inner. Right? If I do something else here, if I do this, it's like instead of conjugating B, I send it here, then that's not inner. And this will be, in fact, an infinite order automorphism also. Yes?
Is the minimum number of generators of automorphism group is known?
The minimum is 2, I believe. But they're not going to be nice. You have to make them complicated. I think there is I didn't put out all the notes I have. But maybe that's it. Is that in exercises? Maybe not. I don't remember if I put it in exercises. When the rank is at least 4, then I believe you can. There's a generating set consisting of just 2 elements. But they're not as simple as this. These are simple generators. But then there are many of them. But this is like, a symmetric group can be generated by 2 elements. Do you know that? Does everybody know this? So symmetric group can be generated by 2 elements. You just need the swap of A1 and A2, and you need the circuit permutation. And then you get everything. So it's just kind of the same spirit. If you make your individual elements more complicated, then you need fewer of them. Okay, so I think this is probably a good place to stop, and then tomorrow I'll start with outer space.